Hello, I'm Shaumek, and I'll be presenting our work, Multiscale UNet with Self-Constructing Graph Latent for Deformable Image Registration. I have no financial interest to declare. Image registration is the process of aligning two or more images into one coordinate system. It can be rigid or deformable. Traditional methods might be slow, which can be a hindrance in many applications. This can be addressed using deep learning-based techniques. Several methods like Voxelmorph, ICNet, FIRE have been proposed over the years, which show good performance, but they do not explicitly encode the overall anatomical view, which might improve the performance further. Moreover, sometimes they face difficulties in tracking different amounts of deformations in the same image. We aim to tackle these issues in this research. Here we are proposing MICTR, which performs the registration in two different scales. We hypothesize that this should assist the model in tracking different amounts of deformations better. We also use inverse consistency, which means registering both the fixed and moving images to each other, which would improve the quality of the deformation as shown by ICNet. At the heart of the MICTR approach, we have our proposed MSCG UNet. This model is an extension of the UNet architecture used by Voxelmorph. This is a multiscale UNet architecture with a self-constructing graph network at its latent. We hypothesize that incorporating SCGNet would help the network encode the overall anatomical view better. To evaluate the approach, we have used IXI T1 weighted images for intramodal registration and IXI T1 weighted as well as T2 weighted MRIs for intramodal. 200 volumes were used for training and 50 volumes for validation. The total loss is a combination of three different types of losses: similarity measure, smoothness loss, and SCG loss. Normalized cross-correlation is used as the similarity measure for the intramodal task, while normalized mutual information is used for intermodal. These losses are calculated on the original as well as on the downsample data for the multiscale approach. Plus, they are calculated in both fixed to moving and moving to fixed directions for the inverse consistency. The total loss was optimized using the ADAM optimizer with a learning rate of 0.0001 for 700 epochs. Now let's have a look at the results. Starting with the intramodal results. The qualitative comparisons of the different models are shown here in the coronal and sagittal views. The results show better similarities with the fixed image than the other methods when we have a closer look at the red, green, and blue regions of interest. The quantitative results also show that the proposed method outperformed the baselines with statistical significance. We further evaluated the generalizability of the method by testing on a dataset pre-processed differently than the training dataset. In this case as well, we see the proposed method perform better both qualitatively and quantitatively. Finally, let's have a look at the intermodal registration results. Here also we can see the proposed method managed to bring the moving image close to the fixed image qualitatively. However, the quantitative matrix do not agree with each other and the differences were not statistically significant. 2 out of 5 matrices used for the intramodal evaluation are not suitable for intermodal. And also, the brain segmentation technique which was used for the calculation of the DICE scores did not perform well, resulting in poorer DICE scores for all the methods. Another point of concern is the blurring that can be observed in output of all the methods. Now to conclude, we have proposed the MSCG UNet model and the MICTR approach, which achieves statistically significant improvements over the baselines for the intramodal registration task, achieving 98% SSIM and 99% correlation. It has been shown that the proposed approach generalizes better than the baselines. In the future, the results might be further improved by adding an additional loss term, the transformer loss. Integrating an affine registration network with MICTR, then training end-to-end might also improve the performance. And the intermodal results might be improved by employing contrast harmonization and treating it as an intramodal task. The code of this research is available on GitHub. Thank you so much for your attention. Please feel free to contact me for any questions or feedback.